Hello. Can you hear me?
Yes, sir.
All right. Okay. So let's get started. Um, going to share my slides. Can you see my slides?
Yes, sir.
Yeah. Okay. So the topic of this session is the microwave catalytic processing. So I think I see the Dr. Anand is in there. So I think that we are not. I think that we are not following exactly the same schedule on the topic because some topic I have to I organize topic for the one session, but it takes two sessions to finish. So today we're supposed to talk about the cold plasma, AI, machine learning, but I think that we haven't finished microwave catalysis process. So I think I'm gonna skip some topic, but I want to go slow, make sure student understand rather than running through my the presentation slide. Okay. So let's talk about the microwave. Yeah, I will talk to Dr. I will talk to Dr. Anand through the email after this session because I think
Yes, sir.
we need to shift the topic a little bit because I did prepare a lot of topic based on the schedule, but some kind of the topic it takes such a long time to interpret it. So because I realized the audience may not have that kind of the knowledge to understand, so I had to spend extra time to interpret. But I'm doing my best to interpret. Again, as I mentioned in the last 3 days, if you have any question, just use the microphone, interrupt me, okay? Don't be so shy. One thing I want to before I'm talking about the microwave, so I can see the audience of the student. So I think at one time I want Dr. Anand to do a quick survey. I know this is very intense. This is very intensive courses. In 2 weeks, every day you have 4 sessions. I think student probably getting tired. I see the audience, the student getting less and less. It's not. I don't think it's a student problem because sometimes if you have the 4 hours a whole day class, you're mentally getting tired. So which is okay. So I want to see the if student is interested in a topic and do my best. In terms of interactive the questions, I tell the truth. I know Indian students very well. When I was postdoc, actually I'm working with when I was postdoc at the University of Pittsburgh, the whole group has a lot of Indian students. Currently, I have 3 PhD students from India. I have 2 postdocs from India. Here's my point. A lot of Indian students and also Chinese students, they don't challenge, they don't ask questions. But I see some audience in the last 3 days, you do ask a challenge question. Please challenge asking challenge questions, which means whatever I lecture here, I'm doing my best telling you either the textbook knowledge or the ongoing research. Those are may not be 100% correct, right? Some of the like we discussed chemical looping and also the plasma. A lot of theory also in the developing. Nobody's correct. That's why academic the research, academic the teaching, you have to challenge the lecturer or the professor. So that's why I'm trying to mention. I do have a lot of Indian students, and then over the year, and then the first year they are pretty polite. Then sir, yes sir. I say no. You don't want to say sir, yes sir. You have to ask and challenge the question. So I say so many things for the audience. When I lecture, if you disagree or you have any new idea, please ask a question. That's whole idea for my I design the topic. I don't design the topic. I just the give you a lecture and then I'm basically run away. No, I want to understand if you understand if there's any new idea or new concept evolve. Make sense? Okay. So microwave microwave catalysis. This is new. So the terminology of microwave catalysis actually you probably using microwave to enable the catalytic reaction. That's the microwave catalysis. You can see this terminology in the literature already. So why microwave? So what's microwave unique? So yesterday we mentioned about microwave, and then we talk about the microwave heating. Yes, microwave heating is one way to understand the microwave catalysis. So it's a different way to utilize the heat or generate heat. For example, conventional heating, you have a reactor. Remember yesterday we talked about you have external heat coming in. So basically, it's a conductive or convective. My microwave is not. Microwave actually is the electromagnetic energy interact with the material, then heat generated. It's not heat to begin with. It's a field. Basically, and it's the electromagnetic field to begin with, interact with the material, then heat generated. Let's take the microwave oven at home. Why why can you heat the food? So I mentioned to you the microwave oven you have at home is basically the 2.45 gigahertz. It's interact with the molecule, all right? So when the electromagnetic field coming into the food, water molecule try to make alignment. Okay, water molecule, you see, if you remember, water molecule is a polar. The water molecule is a polar, and then they try to align with the electric magnetic field. They spin, but they spin, they generate heat because they turn magnetic, no, mechanical energy into the heat energy. It's basically the interaction between the molecule and the microwave or electromagnetic field, then heat generated. To say different way, heat is secondary. The field is first. So you have a field coming to contact with your food. So your container, which is the low density polypropylene or polyethylene, it's transparent. Microwave doesn't care. The microwave sees through, passing through, interact with the water molecule. That's heat generated. Make sense? There's no heat to begin with. It is heat generated when electromagnetic field interact with your water molecule. This is different from conventional heating. Conventional heating, you have heat on the stove burning to begin with. Then you have metal container, conductive or convective. Then you transmit heat onto your onto your food. So I want to repeat. Conventional heating, you have a heat to begin with, then that heat basically transferred onto your subject. Microwave different. You have a field to begin with. You heat generated later on. Okay. So if you understand what I'm saying, how you heat the food at home, you understand this diagram. So basically, microwave irradiation is a field contact with the material. This basically this plain material is, let's say, the catalyst or material. The material, let's say metal oxide, MOM is metal oxide. There's also dipole. Dipole means positive negative charge. When you have a microwave interact with this dipole, just same as a water molecule, they try to make alignment with the microwave, the field. Okay, so if you learn physics, you know every time you have an electromagnetic field coming in, if you have a positive and negative charge, they try to turn, make alignment. The moment they make alignment, so that's basically the kinetic energy produced, heat generated from kinetic movement. So this is how you heat the material. In our case, it's a solid catalyst. Okay, so this is the basic cartoon really show microwave. By the way, microwave does not break in the gas phase. Let's say that you have let's say you have a nitrogen in the gas phase. Okay, so it's a molecule in the gas phase. When microwave passing through air or gas phase, it doesn't break the nitrogen bond. Okay, that's never happened because microwave energy will not interact with molecule. And then only when microwave interact with the material, with the catalyst, then nitrogen react, triple bond get activated. I want to repeat. When nitrogen in the gas phase, sorry, the nitrogen in the gas phase in the path of microwave is not getting activated because it's so stable. And then the microwave energy, if you look at the microwave energy, will not be able to activate this triple bond. When microwave interact with this material called catalyst, Now you basically nitrogen interact with the surface, then reaction taking place. On the right hand side, this cartoon really shows the microwave. Each circle particle is carried particles. When microwave interacts with particles, we found, using the console modeling. If you are, I think, mechanical engineering student, you also use a console modeling. All right. If you do the console modeling simulation, you will see the field, so-called the electrical field between particles, so strong. It's strong enough they can break the nitrogen the triple bond. So that's why I'm saying nitrogen only break on the surface, not on the not the in the gas phase. If you microwave break nitrogen in the gas phase, guess what? At home, you are going to make ammonia. All right? Because in your microwave oven, you have so much air and the nitrogen in there, and you do not smell ammonia. All right? Because you microwave only deal with the dark motor molecule and the, on the on the surface. It's not deal with the nitrogen. Anyway, so all right. So I'm pretty sure that everyone heard about. I want you to see my highlight on the bottom of this decarbonization of industrial heat. So what's the meaning of decarbonization of industrial heat? So that means a lot of people simply say, okay, conventional industrial heat coming from combustion. You combust coal, you combust natural gas, you generate heat. That right? So in the future, I'm not going to do combustion. I want to use renewable power, solar and wind. So a lot of people simply say, I'm going to turn renewable power, which is electricity, into the heat and then heat up the material. That's not efficient. Okay, so if you turn electricity using resistive heating, turning the heat is not efficient. The microwave catalyst we are talking about, we are going to use renewable power. However, we are going to turn renewable power into microwave, and the microwave will interact with the surface active nitrogen. So the co-benefit is basically you are you are taking the electricity, renewable power, in the form of microwave, and then do the catalysis. Either you call selective heating or catalysis. That's my focus on research. It's not simply heat. I'm repeating so many times. If you use microwave as a heat for chemical processing, you are really wasting the microwave. It's not. It's going to be the selective catalysis, or you have to see the co-benefit. Co-benefit means you have to increase the yield, you increase the conversion, increase selectivity. That's what I'm going to talk about. Okay. Any question about theory of a microwave catalysis? The microwave has to interact with the material in order to enable the activation of a CH bond or nitrogen-nitrogen triple bond. Anybody have a question? Raise your hand. I cannot. I think you are on mute. Can you unmute it? It's muted. Yeah.
Sir, yesterday we discussed about microwave catalysis. We talked about catalysis heat, at least alone heated, and then we are sending nitrogen and hydrogen. It forms ammonia. So the continuation of that here, CH breaking you mentioned. So carbon hydrogen breaking.
Yeah.
But yesterday we talked about hydrogen breaking. You know, here CH breaking is mentioned. So hydrocarbon breaking is easy without microwave, I think.
So what I'm saying is, if you the key here is once you have the electromagnetic field, which is a microwave, interact, it depends on the catalyst. If I run through several slides, you will understand. So this is the theory. Only when this slide really show only when microwave interact with the surface, and then let's say methane at the subbound surface or nitrogen at the subbound surface, they can get activated. You follow me? So it's this is really a generic illustration, not necessarily for ammonia, not necessarily for the CH bond activation. This is really how microwave active molecule is not in the gas phase, it's on the catalyst surface. You need a material, catalytic material, to interact with the microwave. Then gas molecule can be activated. So that's on the left hand side. On the right hand side, the same thing, the catalyst. So between the particles, the electrical field is so strong they can ionize the nitrogen. It's more like a plasma, but it's not necessarily plasma. You need a lot of the high voltage to activate the nitrogen. But with the microwave, you do need high voltage. You do need generate plasma. But this field is so strong, you can ionize the nitrogen. Someone call this localized plasma. It's really not plasma. Plasma means you can generate plasma in gas phase. All right. So down here, you generate a localized plasma in a solid phase between the interface of the particles. So there's different activation mechanism. I'm not sure I get your question, but I guess your question is how we activate the molecule. All right.
Yeah. Yes, sir. So actually, plasma we may generate by through microwave also.
Yes, that's what I'm going to talk about next. You can generate microplasma. If you give enough energy, you can generate plasma to begin with. That's what we, as I mentioned, I have a PhD student did that. So there are two ways to generate plasma. One is called hot plasma or warm plasma, which is a microwave. Microwave plasma is not cold. The other way to generate plasma is cold plasma. You just apply voltage, and then the electrons are hot, and then the ions are cold. Yes. But what I'm talking about, this is called microwave catalysis. There's another scenario is called microwave plasma catalysis. That's not my topic today. I think when I get into plasma, I think there's a session on day 4. That's tomorrow. We are going to about different way to mention talk about plasma. This is not microwave plasma. This is microwave catalysis. But microwave catalysis also involve localize the plasma. It's different to segregate. So yeah, microwave plasma is not cold plasma. It's hot plasma because the body of the molecule like nitrogen is hot. Cold plasma, let's say if you generate the nitrogen plasma, only electrons are hot, but your nitrogen is not hot. But microwave plasma, your nitrogen actually pretty hot. The body. Yeah. You follow me? It's different plasma.
Yes, sir. Yes, sir. Got it, sir.
All right. So let's continue on. Okay. So so basically as I mentioned, when you have the let me back up. When I present this in chemical society and engineering society meeting, everyone think a microwave is just a box at home. No, you haven't seen a microwave. Microwave can be very large. And the microwave, the reactor we use, if you see the cartoon, it's no different from the conventional thermally heated reactor. It's continuous flow. It's not box. It's not batch. So I think that this cartoon really shows there's a microwave generator attached to the tubular reactor. We can flow the methane and natural gas or the nitrogen, and we can have different reactions going in, flowing catalyst. We can produce the material. And then I think the question you asked, we can also just use microwave to generate plasma. You preform plasma in the gas phase and flowing through, but that requires different energy. when I say microwave doesn't activate nitrogen, I'm talking about a scenario on the left-hand side. It's called microwave catalysis. But microwave can also run another scenario, 2 operating mode. You can run the microwave plasma and the plasma flowing onto the catalyst. That's a different scenario operate. So today I'm going to focus on microwave only without pre-generated plasma. It's on left-hand side. Okay. So I think the next couple of days, when I have time, I'm going to talk about the right-hand side, how you pre-generate hot plasma, then carry out the reaction. Okay. So anyway, so this is basically the reaction we've been doing in our laboratory. So we have catalyst, and put under microwave, but then we have microwave, and then interact with the catalyst. So in the future, and the future topic, we are going to talk about, we still have catalyst, but we generate plasma. It's called afterglow catalyst. Then the reaction take the two scenarios differently. Okay. All right. So talking about microwave only without plasma, the theory is very complex. So I mentioned about microwave heating. All right. Microwave has to interact with the material. However, microwave heating is very different or very different from the conventional heating. Conventional heating go by the delta T. So which means if you need the center, right at center, let's say 500 degrees C, all you need to do is just keep on increasing the furnace temperature to maybe 800 degrees C, the center will get that temperature. Keep in mind, microwave is a frequency and power. It's really interaction of a field with the material. There's a penetration of a microwave. So depend on the microwave frequency, and there's different penetration. So the deeper the longer the wavelength, the deeper the penetration. All right. So if you're familiar with telecommunication microwave, so that's the basically that's the exactly the same. The longer the wavelength, the longer the distance they can cross. They can cross the mountain, all right, the microwave tower. But if you're too short the wavelength, and then it's different. It's difficult. Typically, microwave the frequency is defined by the from 300 megahertz to the 300 gigahertz. So it's a very wide range. So below the below what you call that below 300 megahertz is called a radio frequency. So I don't want to go through the physics. There are definitions of the microwave frequency or the radio frequency. So, but the physics, the equation I'm showing here, there are a lot of theory behind for the application in the chemical synthesis. There's a penetration of microwave. So if you look at the microwave different, there's an equation shown here. How deep you can penetrate the material is all dictated by this one. There's a frequency, the factor inside here. The dp means how deep they can penetrate. Okay, so that's a penetration, and then talk about the microwave catalysis. So again, this is not the plasma. We don't generate plasma, so that means we use a low power microwave, and then under certain frequency, the microwave catalysis means you have to design the material so become susceptible to microwave. Okay, so this is the different from the conventional heating. Conventional heating, you just heat the material using the conventional, let's say the conductive heating and convective heating. But microwave, you have to design the material, make sure they are sensitive to microwave, so you can induce the activation of the molecule. So that different way to induce the microwave heating or the design of material. One is called the dielectric loss. The material dielectric loss means the material has to have a dipole. That means positive negative charge. The other called conductive loss. Conductive loss means, let's say the carbon nanotube. There are a lot of electrons. They are electron conductive. So it's very easy to heat carbon nanotube using the microwave. The third property of a microwave is the so-called the magnetic loss. So remember, the microwave is the electromagnetic field. There's the E field, there's the magnetic field. They travel together. So the so-called magnetic field also interact with some material. So for example, iron oxide. So the iron oxide actually is sensitive to the magnetic field. So you can heat the iron, the metal oxide, and then under the microwave. So that's the advantage of a microwave. So anyway, so you have to put the three properties together when you design the catalyst. It's different from conventional heating. If you are missing of you can have the property at least has one property. Either that they have dielectric property, that means they are sensitive to microwave as a dipole, or they have magnetic sensitivity. So you have to have at least one property, or you have all three. So they are the sensitive. For example, I think everyone familiar with the zeolite, silicon carbide, all right? Zeolite, you have to be careful. Silica is transparent to the microwave. So microwave reactor we have at in a laboratory, it's coarse tube. Coarse tube doesn't absorb a microwave. That's the whole idea. We want a microwave penetrate the coarse tube reactor. So, so this reactor made by the coarse. Okay. Okay, it's coarse. Coarse, what's the coarse? Coarse means silicon, silica, all right? So basically, the silica is transparent. I think it's coarse, yeah. So basically, silica is transparent to microwave, which is not what we need. Microwave is not conductive, or it's not convective heating. It's a direct delivered energy onto the catalyst. So we do not have any loss on the reactor tube. So the coarse is transparent to microwave. Okay. So now the thing is, if you design the catalyst having silica, it's not going to be microwave sensitive. So we have to modify the zeolite so that it become sensitive. So anyway, so when you design the catalyst, you have to watch the three property to make the material catalyst material. So anyway, so this is design concept. You have an iron component, you have nickel, copper, all kind of the sensitivity, and also you have a carbon support. Carbon support means you have to be the conductive, and also you have a metal and also conductive, and you have the iron in there is magnetic. Anyway, I don't want to go through the process. Normally, when I give this the session to the chemistry the student, I go to very deep. So in the interest of the audience, I don't want to confuse you because there's so much chemistry. You have to have a background knowledge in order to understand. Okay, so I'm not going to downgrade your knowledge, but a different field has different understanding. So, but I want to focus on high level. So low pressure ammonia synthesis. Why? I think as I mentioned, high pressure costs a lot of money to make the reactor, but high pressure will drive a reaction to right. So Haber-Bosch process operate at high pressure. That's the reason, because they want to shift the equipment to the right. Is that right? But it costs a lot of the money. But if you want to use the microwave to operate, remember microwave is coarse reactor. Coarse reactor cannot go to very high. We probably can go to maybe 30 bars if you make the window. Okay, so you have to be instead of operating at 250, 300 bars Haber-Bosch, we want to operate at 30 bars using microwave. That means microwave has to be very efficient to activate nitrogen triple bond. Okay, so that's why the low pressure operations are so important. We do not have advantage of shifting equilibrium to the right, but we have advantage of kinetics. We can make the reaction much faster and have a decent equilibrium conversion. I'm going to pause here. Anybody has any question at this point? My throat was so dry if I keep on talking. Anybody has any questions? If you don't have, I'm going to continue. In day one, I show you this graph, all right? So basically, in US, we build so much solar and wind, and then this becomes stranded, and then we want to turn this renewable power into ammonia and transfer ammonia to East Coast and turn it back into electricity. I don't want to go through detail, but I also mentioned about this, but there's a mismatch of the demand and the supply. So then the project we have is we want to make ammonia, ambient pressure or low pressure. I need to change the title. So either ambient pressure or low pressure ammonia synthesis, because the microwave reactor cannot operate at high pressure. Another reason we don't want to operate at high pressure is, remember, in the Haber-Bosch plant, it takes 3 days to start up, 2 days shut down, because commercial reactor, you have to pressurize the reactor very slowly. It takes time. But if you take 2 days to pressurize your reactor, the solar and the wind can only operate the very limited time. All right, in a single day, you can operate 10 hours on solar. So that's called the intermittent nature of renewable power. So that means Haber-Bosch reactor, so-called steady state operation or 24 hours, 7 days operation cannot be utilized for the to fit into the what you call that renewable power, because renewable power intermittent nature. So you have to have a technology that you can quickly start up and quick shut down. Okay, so that's what I showed you yesterday demonstration. Another problem is scale down the Haber-Bosch reactor from 1,000 tons to match with 100 tons. It takes effort. I sent a slide to Dr. Anand. He's going to distribute. Tomorrow there will be case study. I want the student to read we are going to go through the calculation. So pretty simple. So I basically give you a problem. If you have 100 megawatt, renewable power, let's say solar farm, and then how many you have the 100 megawatt, and then you have the water electrolyzer produce hydrogen, and then I also give you the how much the power needed to produce the 1 kg of hydrogen. So I want the student to do a quick energy balance and also mass balance to tell me with a 100 megawatt solar farm, how many ton of the ammonia you can make per day. It's in this range. I can tell the answer, but I want a precise answer from the student. I want the student to show me the calculation and then how you calculate. It's going to be within this range. It's going to be 5 to 100 tons per day, the range. Okay, it's not going to be 1,000 tons. 1,000. So the point I try to make is with 100 megawatt solar farm, you can only make somewhere between 5 or 100 ton ammonia plant. But if you want to scale down 100 ton per day the plant, and then to this level, you have to scale down 10 or 20 times. Remember, I told you 0.6 power rule. Scale down the large plant technology to smaller. You basically are wasting capital. You basically lose whole the economy scale. Nobody doing that. You are facing the so-called economic hurdle. So that means you have to look for new technology that can handle 5 to 100 ton ammonia plant. It's called a modular technology. What is modular technology? It's basically microwave or the electrochemical. It's not going to be traditional Haber-Bosch process. So anybody have any questions? So tomorrow we are going to do exercise on this. So it sounds very simple based on this slide, but I give you a condition: 100 megawatt, and then how much power to use to make the 1 kg of hydrogen. I want to calculate how much hydrogen you can make and turn that hydrogen into ammonia. So how many tons of ammonia you can make with the solar or the solar farm. Anybody want to say something? Go ahead, please. So anyway, so when Dr. Anand sent you that slide, look at the condition, pre-read it. So I don't want to waste your time because everyone's busy. Every day you spend like 4 hours or whole days to listen to the lecture. So I don't want to waste your time. So tomorrow in the case study, I want to be very efficient and then go through the calculation. Then you make a point. So then you understand why it's so difficult to scale down Haber-Bosch process economically, because you are facing number one, intermittent nature of the renewable power. Haber-Bosch cannot start up, shut down on daily basis. Another economic hurdle is with the largest solar and solar farm or wind farm, and in the range of 5 megawatt or 100 megawatt, you barely make 500 ton for the ammonia, which is the capacity is not even near the Haber-Bosch. To scale down existing commercial technology and to handle this renewable power is no-brain. You are basically wasting your capital. Okay, so that's what I'm going to talk about. So we are going to talk about in a case study tomorrow. I'm pretty sure tomorrow I'm going to lecture 3 sessions, but I want students to be relaxed, and then in the case study, let's go through the calculation using Excel spreadsheet. Okay, I will tell you the answer. It's going to be energy balance and then the mass balance. Energy balance means you have to look at the condition given to you. Mass balance means you have to look at the equation, do the stoichiometry mass balance to come up with how many tons of ammonia you can make. First, you have to do the energy balance to find the hydrogen, then you do the stoichiometry mass balance to find the ammonia. I mean, it's very easy for the chemical engineering student, but for the other major student, you have to probably just sit down and talk to your classmate. Anybody any question before I move to next? No? Okay, let's move on to next. So, all right. So here's what we do. I show you this one. You have a solar and a wind electricity, and then we do electrolysis, hydrogen, nitrogen, and then I talk about this already. So the technology we've been doing at West Virginia University, we have this is the basic microwave reactor. Look at the condition. We can operate at the ambient pressure, 260 degrees C, which is much lower temperature than Haber-Bosch, much lower pressure. All because of the microwave. We can drive kinetic very fast, and then we are not subject to the equilibrium. So I'm going to show you how we did it, why we are not subject to equilibrium control. Okay, so yesterday I showed you a graph. This is another graph to look at this, and so this catalyst. So the key is in this in the microwave catalyst is catalyst material. So I want to go back to the cartoon I show you. I mean, when I give a lecture, it sounds, you may ask, hey, Dr. Hu, you sound so easy. You apply the microwave to the reactor, the magic will happen. No, we spent almost 8 to 10 years now just to design the reactor and design this reactor and design the catalyst. Because catalyst, you have to watch the three property in order to have the microwave susceptible the catalyst. So once you have catalyst, then you can run the reaction. So this is the stability testing of one of catalytic material we are doing. So let's spend a little bit time on this testing. This testing, we tested 7 days, but we have 6 startup shutdown. So the total 80 hours online. 7 days is more than 80 hours, but 80 hours means we are counting online time. So in between 7 days, we shut down, let the reactor sit there and make sure catalyst the back to the ambient condition, and then we start again. So we basically have 6 startup shutdown to mimic or simulate renewable power. So every time we start up shutdown, you can see this horizontal line, and this reaction happened. We did this at 6.5 bar. Yesterday I showed you a 9 days operation, but that's at ambient pressure, but this is at 6.5 bar. Same thing, the catalyst is still stable. So to illustrate this graph, we start at ambient pressure, which is 1 bar. We reach the pressure, but you reach pressure, we all know the ammonia concentration increase because the equilibrium shift to the right, all right? Keep on increasing until we line up at 6.5 bars. Okay, then we quickly drop to the 5.1 bar. Of course, the concentration drop. Then we back to the 6.5 bar, and then back to the normal. So this means the catalyst is stable. Then we hold the pressure for the remaining 6 days. But in between, this dashed line means on purpose we shut it down, make sure they come back. So if you added all the hours together online, that's 80 hours, but we have so much shutdown, and so basically it's very stable. So you may ask me, what's not stable? What's not stable means when the dash line, when you start shutdown, this dash line will go like this. Let me go back to the presentation mode. So for the students who are not familiar with catalyst stability testing, so this graph shows stable. So if you ask me, what if you have catalyst is not stable? Not stable means if you shut down, start again, this line is not going to be here. It's going to be here. And then the next day, you shut down, this line will be here. And shut down here. So this means you failed. Okay, so this means your line is going to be declined like this. That's not good. So this catalyst you got to go back and you design your new catalyst. Okay, so I mean this information for the kind. If you are familiar with the catalysis or material testing, you know what I'm saying. So if you are not, just follow what I said. Stable means you have horizontal line. You start out shutdown, it always go back to horizontal line. But if your horizontal line change like this, that means you have to design your material. It's hard. I mean, I said, I sounds too easy, but actually uh, I would say the microwave catalysis actually is different. It's a little difficult. Okay. All right. So let's go keep on going. All right. So I think let me see. We have probably about the 20 minutes. I'm going to finish this because I'm going to talk about economics as well. Okay. So let's go to this. You're familiar with steady state, all right? So some student may be asking me, so you say so many things about the microwave. What's really unique about the microwave catalysis? So here's the equilibrium curve. Remember, at a given temperature, given given the pressure, reaction will reach equilibrium. Catalyst. Well, let me ask you the audience question. Does catalyst change the equilibrium position? If you learn the high school the chemistry, you should know the answer. And my question is, for ammonia synthesis, if I change the catalyst, does it change the thermodynamics? Does catalyst change the thermodynamics or equilibrium position? I need the answer. Can anybody answer my question? It's very important. Okay. I'm not sure if I share. Can you see my slide here?
Yeah. Yes, sir.
Okay. You can see my slides, all right? So, okay. So you can see my slide.
Yeah. Yes, sir.
Okay. I'm writing my question. Okay. Maybe I'm not clear. Can everyone read my question?
Yeah. Yes, sir.
I need answer. Can anybody tell me? I'm testing your knowledge because if you don't know answer, you don't understand this curve. So can everyone tell me? You should learn this from high school.
Yeah. Catalyst can change the thermodynamics equilibrium.
Can or cannot?
It can change.
So the answer is no. Okay. So the catalyst can only speed up kinetics. Okay. The catalyst will speed up the reaction reach the equilibrium position. The catalyst will not change the thermodynamics. Thermodynamics is dictated by temperature and pressure. Doesn't matter what catalyst you use. So let me put it this way. If you have so basically, if you have this one,
the catalyst only do the reaction.
Yes, the catalyst only help the catalyst equally speed up the forward and the reverse reaction, making this reaction reach equilibrium faster. They cannot shift the equilibrium, the catalyst. Okay, it basically catalyst deal with the kinetic. Okay, let me just say different way. Make sense? I hope I fresh your high school the chemistry. I hope I fresh your high school memory. You should learn it in high school. I think the teacher in high school or maybe the first year college always tell you catalyst only speed up reaction rate, helping kinetics. Catalyst does not change thermodynamics. Equilibrium is related to thermodynamics, not kinetics. Make sense?
Yes, sir. Understand, sir.
Okay. So now, if you understand this, this curve is going to confuse you. Okay. So keep in mind, catalyst does not change equilibrium position, and it only speed up reaction. So this is the equilibrium curve. Okay. The equilibrium curve means we basically you have ammonia concentration. You have, and by the way, this reaction, this curve. We published the paper. I can show you the paper. We published the paper along with the professor from the Florida State University, and then actually he did a lot of reaction. So this reaction is under microwave in a sealed vessel, and then we basically increase temperature, and on the x side is temperature in terms of K Kelvin, and the other is ammonia. So the pressure of this reaction we did in the 1 atm. Okay, so basically you at a given temperature and a given pressure, you have one data point. You change the pressure, you have another data point. So keep in mind, equilibrium only related to temperature and pressure. Okay, doesn't matter related. So each curve we obtain in such a way, you you change the temperature and get a different data point. You plot the curve. So we have three curves here with three different catalysts under microwave. Okay, let me try to emphasize it. Under thermal heated conditions, thermally heated. Thermal heated means you basically using the thermal furnace and then heated and temperature. That's a 400 degree K, 400 K. So under thermal heating, we have one equilibrium line. Okay, this is very important. So it's still controversial. Where's my, okay. So basically, this is 400. So how the equilibrium of 400K. So when you use the thermal heat iron catalyst, you get one data point. So then we basically put in the microwave reactor and then using the ruthenium catalyst, different catalyst, and then the 400K is here. So then we change the catalyst, change it back to iron catalyst, but under microwave heating, it's here. Same temperature, okay? You see the point? The same temperature, different catalyst. We have three different equilibrium positions. Remember, if you open the chemistry book, catalyst does not change equilibrium position. Catalyst only helping the kinetics. So there's no kinetic issue because we are measuring thermodynamics. So question is why we have a three position. So in theory, if microwave and thermal heating are the same, there's three lines, red, green, and orange line should be overlapping. It should be same line because doesn't matter how you change the catalyst, doesn't matter how you use the microwave or thermal heating because you are operating at the same pressure, ambient pressure, and the same temperature 400 degrees C. You should only have one data point. You should not have three data points. I know this was so complicated for the audience, right? Because I apologize this because I used to lecture this for the catalysis community, but for the audience you have, it's very difficult. But I'm trying my best to interpret to you what the difference is between microwave and thermal heating. So the basic you change the equilibrium position. Okay. So we published this. If you are interested, I can show you the paper. I think I'm going to stop here because I'm getting too complicated. So microwave. So if you want to know why microwave change equilibrium, there are a lot of theory behind. So the thermally you heat it at 400K, a microwave heated at the 400K, but that's the 400K temperature is so-called global temperature. But microwave is slightly heating, so it's non-equilibrium. Even if we measure under the equilibrium condition, we think we reach equilibrium, but the microwave actually they never reach equilibrium because on the surface it's constantly changing the different temperature range, and then it's constantly the equilibrium change. So I apologize, so complicated. I'm going to stop here. I'm going to move to the next. So should we stop here or wait for the tomorrow? You want me to continue? So I have a lot of slides today. So should we? Because the next slide will be talking about economics and also basically I think yesterday some students asking questions. What if you don't use hydrogen? Use the method? Yes, you can make ammonia using this way. I'm going to save this for tomorrow because it's so complicated. I don't want to rush through this slide. I need a time to interpret to this table, economics table based on iceberg simulation, and then also the how we are going to react with the method with the nitrogen without using hydrogen. There's a lot of the theory behind. I'm going to stop here if you agree. So maybe I should pause here, waiting. So today I'm talking about the microwave catalysis. Tomorrow I will continue talking about microwave catalysis, but there'll be the different angle to see the benefit of microwave. Okay. Anybody have any question before we conclude finish today?
One question before the end of the session. One question
again?
Participants.
Yeah, any question before we end today's session?
Yeah, okay. Only one question. After that, we can close the session.
Okay.
Only one question.
What's question?
Yeah. Hello, sir. Actually, microwave catalysis we looked today, sir. In that, if microwave is not if catalyst is not accept microwave or observe microwave, then we can't use as a microwave catalyst, right?
Yeah, you are right. I think this same question has been asked in the conference. I wouldn't say microwave is magic. Okay, a lot of people 20 years ago when microwave has been applied, well, microwave was discovered in 1940s, but only applied to the catalysis was 20 years ago. But 20 years ago, people abused microwave. They think, oh, microwave is magic. They can induce any chemical reaction. That's not true. So in the last 10 years, if you track my publication, my group on West Virginia University, along with the National Laboratory, Pacific Northwest National Laboratory, and also the National Energy Technology, the National Laboratory, we work together. We try to reshape microwave, and also we also team up with an international team. Okay, like some Japanese group, we invite them to give a conference lecture. So we try to make sure people do not abuse microwave. Don't try to say microwave is magic. So to answer your question, microwave is not magic. You have to design the material so that the microwave is sensitive to the microwave. Then you can enable the microwave catalysis. Okay, if you don't have that material, microwave is nothing. Basically, you cannot even. So, for example, if you use microwave, have a plastic container, microwave will not even heat that container. Is that right? So that's to give a very good example. Any plastic will not be sensitive to microwave, which can be good or bad. Is that right? But good news, the plastic means you can make the microwave the container heat your food. That will not be damaged. But if you use the plastic as your reactor, it's not going to work. All right? Or for the polymer, it's not going to work. So to answer your question, the material that has to be induced by microwave by all means, like that three parameter I show you. So the material has to be dielectric, sensitive, conductive sensitive, or magnetic sensitive. So I hope I answered your question. So it's not magic. You have to be, so basically, to summarize what I say today. Microwave catalysis is a combination of microwave, electromagnetic, and material science. And then by putting material science and the microwave electromagnetic field together, then you apply it to catalysis or chemical synthesis. Make sense?
Yeah, yes, sir.
Yeah. So we will continue tomorrow because I don't want to rush through my slides. I have so many slides going on, but I save slides for tomorrow because this table takes me time to interpret to you. I think some students asking high pressure cryogenic condenser to separate ammonia is very expensive. Yes, for high pressure Haber-Bosch process, you have to use the higher pressure condenser. Now, keep in mind, we lower the pressure using microwave already. We are not going to go back to use high pressure condenser. Is that right? Does it make sense? Is that right? So if you have low pressure operation, the back end has to change accordingly. Is that right? So this basic cartoon will tell you that different technology we can basically integrate with the microwave. So we change completely the Haber-Bosch process. So this cartoon shows economic analysis, how we compare with Haber-Bosch. We really save a lot of money economically, not just like a technically. Okay. All right. So let's stop here, and then tomorrow we continue on economic, and then so we shift a little bit to the nitrogen reactive hydrogen. Remember, in the Haber-Bosch plant, you have to reform the methane into hydrogen, costing you 50% of capital. Now, by using microwave, you basically bypass the steam reforming. You save at least half operating cost, half capital cost. You can make ammonia and then also the ethylene. So I have a student, a PhD student. Actually, she's from India. She went back to India, so she got PhD. Now working for the Honeywell. I think Honeywell India. So that's a very good company. So yeah, okay, all right. So I think in the interest of time, let's stop here. I will see you tomorrow. I think Dr. Anand, tomorrow there are three sessions, all right? So there's one session I'm going to do the so-called case study. I'm going to go through how you calculate, from the renewable power, how much ammonia you can make. Then we come to the point and the discussion. Okay, you can only make such little ammonia, Haber-Bosch cannot scale down, and then what option we have. Would that be good? So I'm waiting for you to send me the 3 links for tomorrow. Okay, Dr. Anand.
So we have really enjoyed your lecture, and we'll meet tomorrow. And thanks for joining today.
Yeah, okay, yeah.
Thank you.
Thank you, everyone. See you tomorrow. Okay. Yeah, okay, bye.